Hello, good day to all of you. Welcome once again to our online training. Today, we are going to discuss the logic gates used in electronics. But before that, we have to give you the past lesson. Here it is. In our review, we already had the binary. As we defined that the binary is a number system with the base of 2. So that means that we are using only digits as 1 and 0. 0 corresponds to 0 volt and 1 corresponds to 5 volts. That means that any device or the indicators like lamp or any device containing 5 volt supply will activate when it is in 1. If there's no voltage exists, so that means the output is 0. That means that if it is 1, considered as high, and 0, that implies low. It also implies 1 corresponds to yes, and the other is that 0 corresponds to no. It also implies that 1 corresponds to on and 0 corresponds to off. 1 corresponds to close and 0 corresponds to open. There is the notations in digital system. The bit is considered as short for binary digit as numeral value. That's why it is bit. 1, it's either 1 or 0. 4 bits correspond to we call this as nibble. If there are 8 bits, that means it is equivalent to byte or 1 byte. So that means 8 bits equivalent to 1 byte. If we have 16 bits, we call this one as word. So 16 bits or 2 bytes equivalent to 1 word. If we have 32 bits, we call this one as double word. This 32 bits composes of 8 bits. It is equivalent to double word. If we have 64 bits, we have the quad word or a paragraph. Okay. There are simple circuits we can conduct in making this circuit as simple. It is more than that, we can make it complex. 2 or more simple circuits can be constructed as one complex. A switch, a single switch, can be used in operating as a particular device. But if we need more than 2 switches, we can use this in switching digital circuits or a computer, a simple computer. Or more than that, if it composes of the computer or microcontrollers and different kinds of circuits, we can create a robot. There is a place value in binary number. LSB and the MSB. LSB means least significant bit can be found on the right side of the binary number, while the most significant bit can be found to the left side of the binary number. For example, okay, so with the binary number 1, 0, 1, 0, so there are 4 bits here. 1 bit, 0, 1, 0. So as I have said, that the LSB can be found on the right side here. This is the least, so meaning the value is lesser, while the most significant bit can be found on the left side of the number. Okay? So here, from this side, from the first bit, it is equivalent to 1 in the decimal number. So if you place here 1, so that means the equivalent value for this is 1. And the bit or the second bit next to the first, going to the left, this one, corresponds to 2 in decimal number. So it is equivalent to 2. So that means 1 and 2. So for this time, 1 and 0, that means there's the presence of number 2 without 1. So the equivalent for this 1, 0 is only 2. But if in case this one is 1, 1, that means you have to add 2 and 1. It becomes 3. Okay. The third bit is equivalent to 4 in decimal number. So if I have here 0, or for example, I have here 0, 1, 0. So there is 0 here. So that means no need to add 4. So we just have 2. 1 here is 0. So still, it's not changing. The fourth bit has 1. Here, the fourth bit, the equivalent in decimal number is 8. And the fourth bit. So that means the equivalent of this binary number 1010 is equivalent to 8 plus 2. So that means is 10. So this is the table for the counting numbers as 0 going to 10. 0, 1, then 2 is 1, 0, 3 is 1, 1, 4 is 1, 0, 0, for number 5 is 1, 0, 1, for number 6 is 1, 1, 0, for number 7 is 1, 1, 1, and guess, we have here number 8 for the fourth bit, so we have 1, 0, 0, 0. For number 9, 8 plus 1 is 9. So the bit is 1, 0, 0, 1. Okay, once again, how to get 10? So that means 8 plus 2 is 10. So that's why the figure for the bit is 1010. So let us proceed to our new lesson. I'll be giving you the lecture for the basic logic gates. At the end of these lessons, we have to understand the basic principles of the logic gates. Identify the basic logic gates, and we would be able to draw the schematic symbols in the circuit. Express the output in the truth table. We will be using a truth table in each of these logic gates. Which way do you think is good? For sometimes you are traveling. Which way you are going? To the left or to the right? But before you plan to go on a trip, you have to know the direction. So that means you have the basis on where to go. Where you're going, to the left or to the right. So that is a decision. It is a way of making a decision. You have to think. Okay? So there are references of your thinking. You have some past lesson in order to understand the succeeding lessons. Let us think. What do you think? What do you mean by logic? Logic means it's a judgment. It is a reason or order. It is also a sequence. Might be a decision or common sense as thinking. Then, what is gate? Gate means it is an entry, entrance door, gateway, or opening. But we combine this logic and gates. What is the meaning? So logic gates are devices used in making a decision in digital systems. Inputs are said to be stimulus and output that used to have a response. So that means there should be a trigger in the inputs before responding to the output. A logic gate is a building block of a digital circuit. Most logic gates have two inputs or more than, and one output, and are based on Boolean algebra. Later on, we will discuss the Boolean algebra, which may help us in discussing these logic gates. At any given moment, every terminal has two binary conditions. It might be number 1 or number 2, or might be high or low, or might be false or true. False corresponds to 0 and true corresponds to 1. Different types of logic circuits can be used, and the combination of inputs and the binary outputs will differ depending on your purpose. A logic gate outputs can be thought of like a light switch, wherein one condition is off and in another it is on or 1. Logic gates are commonly appeared in the form of integrated circuits. So let's start. This is a symbol for the NOT gate, or it is so-called inverter, where the inputs opposite to the outputs. It is also known as inverter as I have said. It is to differentiate it from other type of electronics inverter devices. It has only one input. It reverses the logic state. For example, if the input is 1, therefore the output is 0. If the input is 0, the output is 1. Okay? So we are just inverting the input. So if this is the input A, is the input, this will be the output. So if I have here the 0, so this one, the output will be 1. If the input is 1, then output is 0. Anything that connected to this inverter will come as input 0, the output will become 1. And 1 will become output of 0. So in this circuit, if it is contact 1, if it is 0, then the output is 1. And if it is 1, the output is 0. OR gate. This is the symbol for the OR gate. It gives a high output if one or more of its inputs are high. A plus sign is used to show the OR operation. That means any inputs among those input signals here, it might be 2 or 3 inputs, the output should be 1. But if all of the inputs are 0, that means the output is 0. Let us refer to the truth table. If inputs A and inputs B are 0, 0, 0, that means it is 0. As I have said, just 1 or all the inputs are 1, the output is 1. But if all the inputs are 0, the output is 0. So if I have here 0 and 1, the output is 1. Or might be 1, 0 inputs, so the output is 1. Okay? In our illustration, so as you can see in the circuit, it is like a parallel circuit for a single light bulb. So any one from the switches is contacted to the lines. So the electricity is connected towards the light, it would be able to light the bulb. So anyone. So that means the connection is similar to a parallel circuit. So the symbol is here already for the input and the outputs. The same as this circuit. So in this case, we join the inputs of the OR gate. So whatever you put in the first input, then the other one is just joined. So if I add here 1 the other input will also be 1. So that means the output is 1. So no changes at all. Here's another gate. This is called AND gate. It is somewhat different in the figure of the OR gate as compared to AND. Just be particular with the symbol. AND gate, where the output that gives a high output only if all its inputs are high. A dot or operation in multiplication, X, is used to show the AND operation in or omitted. For example, here Y as output is equal to A ANDed B. We can use here a dot, or might be X, AXB or A dot B, or omit the dot or X. But the meaning is just the same. So as I've said here, only if all inputs are high, the output is high. Let us see. Look at here, the inputs A and B. If it is 0, 0, the output is 0. 0, 1, still 0. 1, 0, the output is 0. But if the output inputs are 1, 1, so that is the time the output will become 1. In the circuit, it is similar to a series circuit of switches before going to the output of a light bulb. So, if one of the switches is on, but the other is not, so there's no way we can open the light. We can turn on the light. See here. So on the other side is 0, 1, it's still not working. If it is 1, 0, it's not working. But if you turn on both of the switches, this will turn on. Another kind is NOR gate. NOR gate is almost similar to OR gate, but the only thing different is that there is a bubble in the output. This bubble in the output corresponds to the changes of the output, or equivalent to the inverter gate or the NOT gate in the end. So that means the OR gate will just combine with NOT gate in the end. It is equal to an OR gate followed by a NOT gate. The output is low if any of the inputs are high. It is just a reverse of the OR gate. The symbol is an OR gate with a small circle on the outputs. The small circle represents inversion. So that means we'll just invert. If you will recall before, in OR gate, any of the inputs is 1, so the output is 1. But you will reverse the output in that case. So 0, 0 will becomes, in OR gate is 0, invert is 1. In the OR gate, 0 and 1 is 1, invert the answer, so it will become 0. So the rest will becomes 0. Another gate is what we call the NAND gate or the NAT AND gate. It is equal to an AND gate followed by a NOT gate. The output of the NAND gate is high if any of the inputs are low. The symbol is an AND gate with a small circle on the output bubble. The small circle represents inversion. As you will recall in our lesson in the AND gate only turns on when all of the inputs are 1. That means it will become 1. But for now, it is inversed. Okay? Just reverse the answer. So if it is 0, 0 in the AND gate, should be 0. But reverse. Invert the answer, it becomes 1. 0 and 1 in AND gate is 0, but invert the answer, it is 1. 1 and 0 in AND gate is 0, invert the answer, it is 1. But 1, 1, it should be 1 in AND gate, but invert the output, it becomes 0. So here are the symbols of the NAND gate and the NOR gate. The NAND and the NOR gates are called universal gates, since with either AND or OR functions and NOT can be generated to these gates. So we will do this in our succeeding lessons. Here is another kind of gate. We call this one as the XOR gate. So it is similar to the OR gate, but there is additional line at the back of the inputs. Okay, so there is a plus sign, there is a bubble with a plus sign inside. The XOR gate, the output is true if either input A is true or input B is true, but not when both of them are true. This is like an OR gate, but excluding both inputs being true. So the sequence is that it should be different in inputs. It should be 1. It might be the other one is 1 and the other one is 0. So it will becomes 1. So both 0, 0 is 0. If it is 1, 1, the output should be 0. The only thing, it should be different. So that is the special purpose of this XOR gate. Exclusive. Okay, so in the next activity, we will be combining these gates in order to make a decision in circuit. Okay, we can acquire the ability to combine these gates by using our logic gates. So I will guide you in the past lesson. Okay, just this ends our lecture. Thank you very much.